Thank you. Good morning, ladies and gentlemen. My name is Stephen O'Neill, and today I'm going to be talking about an exciting new drug that could reduce organ injury in kidney transplantation. Kidney transplantation is a life-saving operation that is by far the best treatment for kidney failure. However, following a transplant, up to 40% of patients may be affected by delayed graft function. This means that they need post-operative dialysis. This problem is particularly common in kidneys that suffer prolonged ischemic injuries. Reducing ischemia reperfusion injury is therefore absolutely key to better outcomes in kidney transplantation. Our research group have previously shown a reduction in this injury in mice pre-treated with drugs known as heat shock protein 90 inhibitors. The drugs used were gildanomycin, abbreviated to GA here, and its analogues 17-AAG and 17-DMAG, but both these drugs are poorly tolerated by patients. We have therefore begun working in collaboration with Aztecs Pharmaceuticals on an exciting new drug called AT13387. It also binds to the N-terminal of heat shock protein 90, but it's a much faster acting, smaller molecule heat shock protein 90 inhibitor. It's also got a low toxicity profile in phase 2 studies in oncology, and therefore has excellent translational potential. Currently, the mechanism of protection offered by this drug remains uncertain, and defining how AT13387 works is crucial for its further development. In ischemic kidney injury, damaged molecules like hyaluronan are released. These then bind to a very important cell surface receptor called TLR4. This in turn activates a pro-inflammatory mediator known as NF-kappa B, and this results in kidney injury. Looking at this point in the pathway in slightly more detail, when TLR4 is engaged, it activates an enzyme complex called IKK. This then upregulates NF-kappa B, resulting in pro-inflammatory cytokine release. The IKK complex may need heat shock protein 90 to stabilize it. Therefore, treatment with heat shock protein 90 inhibitors, like AT13387, may destabilize the complex at that point and prevent the rest of the steps in the process, ultimately leading to cellular protection. My hypotheses were that in vitro, AT13387 would reduce this inflammatory signaling in kidney cells and increase cell survival following oxidative stress, while in vivo, AT13387 would improve kidney function following ischemia reperfusion injury. To begin proving my in vitro hypothesis, which I've presented in stepwise fashion down the side of my slides, I began working with human embryonic kidney cells, abbreviated here to HEC293. This is a non-cancer cell line that I suspected would express low levels of TLR4. And using flow cytometry, I was able to confirm that these cells do not express any more TLR4 than negative control samples. I then transfected some of these cells so that they would express TLR4, and flow cytometry on these cells confirmed that they had greater than 95% cell surface positivity for TLR4. So this meant that we had identical cells, but with vastly differing levels of TLR4 expression, and I could selectively express TLR4 in my next experiment. In this experiment, I inserted a reporter into the cells that reflects hyaluronan-mediated NF-kappa B inflammatory activity. I found that in cells with TLR4, there was an increase in inflammatory activity following hyaluronan stimulation. The addition of a drug called polymyxin B, which clears endotoxin contamination, had no effect on this result. However, in cells without TLR4, there was no inflammatory activity. This meant that hyaluronan was a sterile activator of inflammation and was only acting through TLR4 in my cell system. I then pre-treated the cells with the heat shock protein 90 inhibitors, AT13387 and 17-DMAG. I then stimulated the cells with hyaluronan, after which I performed Western blots for the 3 subunits of the IKK complex, alpha, beta, and nemo, which is also known as IKK gamma. Beta-actin was used as my loading control in these experiments, and compared to DMSO vehicle, both drugs, but particularly AT13387 in green, led to a loss of all 3 subunits of the complex. Compared then to cells that were not pre-treated in red or pre-treated with DMSO vehicle, This drug-induced loss of IKK led to a dramatic reduction in inflammatory activity following hyaluronan stimulation, particularly in those cells pre-treated with AT13387 in green. In fact, AT13387 reduced inflammatory activity to the level of resting cells simply left in basal conditions and represented here in purple. I then performed a cytokine array panel. The dots in this panel represent in duplicate the expression of a range of cytokines. And compared to pre-treatment with DMSO vehicle in the upper panel, pre-treatment with AT13387 led to a reduction in the secretion of a range of cytokines following hyaluronan stimulation, including a number of pro-inflammatory cytokines, such as GRO-alpha, which is number 2 on the grid, and IL-8, which is number 4 on the grid. I then tested whether this would lead to in vitro protection. I did this by pre-treating the cells and then exposing them to oxidative stress with hydrogen peroxide, an insult which kills cells. Cells simply left alone in basal conditions in purple, or pre-treated with a DMSO vehicle but not given hydrogen peroxide in light blue had 100% cell viability. When hydrogen peroxide was given, cells that were not pre-treated in red or pre-treated with the DMSO vehicle in dark blue had a roughly 30% decrease in cell viability. However, when AT13387 was given, it significantly improved cell viability, including in comparison to 17-DMAG, which is the result highlighted in yellow. To then test my in vivo hypothesis, I used an established model of ischemia-reperfusion injury. In this model, mice are pre-treated with AT13387 6 hours before I remove the right kidney and clamp off the blood supply to the left kidney with a titanium clip. After 20 minutes, this clip is removed, and it produces an injury that is very similar to that sustained by a transplanted kidney. And the outcome measure I look at is serum creatinine after 24 hours. AT13387 significantly improved the function of the kidney. This was determined by a significant reduction in serum creatinine compared to vehicle-treated mice 24 hours after this injury. In fact, AT13387 returned serum creatinine to a normal range in mice that were pre-treated by this drug. Therefore, in conclusion, I have addressed and proven my hypotheses that AT13387 protects from oxidative stress in vitro and renal ischemia-reperfusion injury in vivo. I've highlighted that the mechanism of protection may involve a potent anti-inflammatory effect. And finally, I would like to just emphasize that AT13387 is a new drug with excellent translational potential. Thank you.